Hello, guys. Say, okay, 9 now. Okay. All right. So let's continue from where we stopped. First of all, last week I had issue with there is connection issue, I think, throughout the campus. I couldn't make my class. Like I said, I will make it up. So today, after this class, I will schedule another one. So those that may be available should attend, and those that will later want to watch the video will definitely be available on the Blackboard. Okay. So last week also we were asked to create a video for the lectures on Wednesday because of the National Day. So we were asked to create videos for all lectures on the day and upload. Okay. So I didn't do that yet, but I will do it also. Okay. So today and tomorrow, today is 1 hour lecture, and then after that, I will create another lecture to make up for what we missed last week. Okay. So let's quickly move to where we stopped, and we can finish up with this chapter 2. I've spent so much time here. So, as you may recall, we have vapor pressure, okay, which we said is the pressure at which liquid will rise or boil at a given temperature. Okay, and let me put it in this presentation mode so that I can write. This is like 80. Yeah, we have explained all this. Vapor pressure, that it is the pressure at which liquid phase and vapor phase thermal equilibrium, meaning there is no net transfer of heat energy. Okay, so as the external pressure on water reduces, vapor pressure reduces according to the point. Accordingly, the boiling point of water reduces. So I asked a question: that is it better to cook in Jeddah than in the Himalaya? Jeddah is at sea level. Himalaya is a mountainous region in Asia. Okay, it's a mountainous region. So meaning in Jeddah, you have the pressure to be atmospheric. Himalaya, because it's mountainous region, so you have high mountains. And on top of those mountains, you have the atmospheric pressure to be reduced. Because the higher you go, the less the atmospheric pressure. It reduces with altitude. So that implies the external pressure acting on water reduces when you are boiling or when you are heating water on the Himalaya. Okay. And what that means is that water boils faster in Himalaya than in Jeddah. Okay, if it boils faster, what does that mean? Let's assume, the boiling temperature now, we know the normal boiling temperature at standard atmospheric pressure is 100 degrees centigrade. Okay, so you have 100 degrees centigrade at 1 atmosphere, which is, this corresponds to the situation in Jeddah. Then on the Himalaya, let's assume the pressure reduces, I don't know the exact value, but let's assume the pressure reduces to, let's say 0.8 atmosphere. And the boiling temperature definitely will change. It will reduce now because there is less pressure acting on the surface of the liquid. Okay, so the boiling temperature, let's assume it reduces to 80 degrees. Just assumption. Okay, so what does this mean? You know, water cannot, uh, uh, it has to be at a different phase. Okay, once it reaches the boiling point, then it has to vaporize. Okay, it cannot go beyond that. Okay, of course, you have superheated water, supercritical water that can, which is in, that can be boiled, but that is for industrial processes and other stuff like that. But under standard conditions, once water reaches the boiling point, then there must be a phase change, okay, from liquid to vapor. So meaning the temperature is 80 degrees, yet it is boiling. And for cooking, you need high temperature to quickly cook your food, okay? So meaning it will remain at 80 and you have to slowly, sometimes it will not reach the 80 degrees because if it reach 80, it will vaporize and become vapor. So you may have to cook at even lower temperature, let's say 60, 70, thereabout. And that will take longer before your food gets cooked, okay? So it takes longer than necessary. While in Jeddah, because boiling point is 100 degrees, so you may cook your food, let's say at a temperature of even, is it 190 thereabout. So you get more heat. The heat is higher, hence your food will be cooked at a faster rate. Okay, while on the Himalaya, because of limit, because the boiling point has reduced, so when you try to cook at 90 degrees, you will find no water in your pot because all the water must have vaporized. Okay, you don't go beyond 80. Okay, you don't go beyond 80 because once it reaches the boiling point, it vaporizes. Okay, while in Jeddah, you can go beyond 80 because the boiling point is up to 100 degrees. Okay, so I hope this explanation is clear. Vapor pressure is called the saturation pressure, and the corresponding temperature, the saturation temperature. Okay. So, however, time required to reach vapor pressure is much higher in conditions with higher external pressure. I think this is also the explanation of the Jeddah Himalaya regions. Okay. And this boiling can reduce performance and damage equipment. Okay, boiling can reduce performance and damage equipment. We will explain the application of the vapor pressure very soon to engineering structures. Okay, thus engineers need to be able to predict when boiling will occur, because as we are going to see in the case of cavitation, okay, flow in pipes, once the pressure in the pipeline reduces below the vapor pressure of water, okay, once water pressure reduced below its vapor pressure when conveyed in a pipeline, then cavitation occurs, okay, which leads to the formation of bubbles. The bubbles, once they reach higher pressure, they burst, and when they burst, they attack the material, they attack the pipe material, so they cause some scouring effect. Okay, this we are going to see. This prediction is based on vapor pressure. Can you see the next slide? This is slide 81. Predicting boiling using vapor pressure. Can you see it? Oh, it's not showing. Okay. Someone is asking, do you need to be present lecture at on 9? No. For the makeup lecture, you don't need to be present. I say only those that are available. Only those that if you are free, then it may be good for you to be available, because by that you must watch the video, because what I will cover, I will not cover it again in another class. Of course, in the next class, I can take questions related to the video that I will, the lecture that I will record. So if you are free, I mean, It doesn't take anything. So you just come in and then you listen. If you have question, if you are not ready, then you can watch it later. But you must watch it later. You must watch it because whatever will be covered in the lecture will not be covered again. Okay. Yeah, this is really um, having issues. Okay, so now predicting boiling using vapor pressure. The pressure at which a liquid will vaporize or boil at a given temperature, we said is called the vapor pressure. This means that boiling occurs whenever the local pressure equals the vapor pressure. Whenever the local pressure equals vapor pressure, then boiling will occur. This is how to predict boiling, and this is the condition for boiling. Whenever the saturated vapor pressure is equal to the standard atmospheric, okay, which is the local, which is the local pressure in this case. Vapor pressure, let me see. Okay, vapor pressure increases with temperature. Okay, it increases with temperature. Of course, we should expect that the vapor pressure will increase with temperature because the more heat, the more energetic the particles in the fluid is to move, to break apart from the liquid to the gaseous phase. Okay, and that's why the pressure will now increase because you have more of the molecules, so they will exert more pressure. More pressure is temperature. So now, between open and closed containers, receiving heat, which one boils fast and why? Okay, let's say you are boiling water to take a tea. Okay, or you are boiling water, to cook something. When you close the container, you have one that is closed and one that is open. Which one do you think will boil faster? Okay, okay? Which one will boil faster and why? Definitely the one that is closed will boil faster because of the fact that the vapor is trapped. Okay, the vapor is trapped, hence they will exert more pressure on the liquid. So the vapor pressure will be higher than the one in which the cover of the container is not there, or than the one in which it is open. Because one in which it is open, I told you evaporation, takes place at all temperatures. Okay, but when heat is supplied, evaporation is faster. Okay, it becomes faster. So when the liquid from the water phase changes to the gaseous phase, they escape to the atmosphere. So the vapor pressure is not comparable to the one in which the vapor is trapped inside, the space between the water surface and the cover of the container and the lid. So that one in which it is covered, it will exert more vapor pressure. And once it has more vapor pressure, it means it can quickly reach the atmospheric pressure, which is the condition for boiling to occur. So this is the reason why closed containers usually they will boil faster than open containers, because in closed containers vapor is trapped, hence it exerts more vapor pressure than the case in which it's open, because that one the molecules escape, hence it exerts less vapor pressure than the container which is closed. Okay, it is clear. Another way, boiling can also occur in water at temperatures much below 100 degrees Celsius. I just explained the Himalaya and Jeddah case, in which in Himalaya, because of the high altitude that you have, the atmospheric pressure is lower. The vapor pressure, boiling occurs when the vapor pressure is equal to the atmospheric pressure. In Jeddah, the atmospheric pressure is 1 atmosphere. So the vapor pressure has to be equal to 1 atmosphere before boiling occurs. In Himalaya, the atmospheric pressure is less than 1 atmosphere. Let's assume 0.8 atmosphere. So the pressure should be equal to 0.8 atmosphere before boiling occurs. Okay? And that means in Himalaya, the boiling temperature will be lower because the vapor pressure is lower. Once the vapor pressure, once the atmospheric pressure is lower, then it takes less time. It takes less amount of heating to reach the atmospheric pressure. Hence, the boiling can occur at lower temperature. Okay. If the ambient pressure is reduced to the vapor pressure of water, boiling occurs at in lower pressure. Of course, when you reduce, this also still in line of what in line with what I have explained. Okay, for example, water boils at 134 degrees in a pressure cooker, operating at 3 atmosphere. 3 atmosphere, that's 3 times the atmospheric pressure. So definitely we would expect the boiling point in that case to be higher. Okay, but it boils at 93 degrees in an ordinary pan at a 2,000 meter elevation where the atmospheric pressure is 0.8. Yeah, this is exactly my point. You know, in atmospheric pressure, so water boils at 100 degrees Celsius. Okay, but let's say at 2 kilometers above the sea level, the atmospheric pressure has reduced to 0.8. And when it reduces, the boiling temperature will also reduce to 93 degrees centigrade. Okay. Now, let me show in the change. Okay. Now, this is showing the saturation of vapor pressure of water at various temperatures. Okay, the vapor pressure is in kilopascal. So you can see at various temperature, as the temperature of water increases, so is the vapor pressure. At 100 degrees, you have the vapor pressure to be 101.3, which is the atmospheric pressure. Okay, of course, when the boiling temperature, or when the vapor pressure increases, okay, you have the atmospheric pressure also to be increasing. So what this means is that if you want to boil water at 50 Celsius, what do you need to do? All you need to do is to reduce the local pressure, atmospheric pressure, to reduce it to 12.3, from 101.3 kilopascal to 12.35 kilopascal. And once the local pressure is reduced and that temperature, water temperature is at 50 degrees, then it will begin to boil. Because at that point, the vapor pressure will be equal to the local atmospheric pressure. And once the local atmospheric pressure is equal to the vapor pressure, boiling occurs. Boiling is simply the formation of bubbles. They will be emanating from the bottom, coming up to the surface and burst. And then you have the phase change from liquid to gas. So still on the properties of fluids, if the pressure above liquid reaches the vapor of the liquid, boiling occurs. For example, the pressure is reduced sufficiently, boiling may occur at room temperature. This I just finished explaining. You see in this figure that we have water in liquid form, and we have the vapors, escaping from the surface. So if the surface of the water is closed, the vapor escaping, okay, they will not escape per se, but they will come back to the liquid. Okay, so that is when we say saturation occurs. That is, you have molecules, equal molecules vaporizing, equal to the molecules returning back as liquid. Because once they can't escape, they will go to the lid and they condense. Once they condense, they will come back to the, they will become liquid and fall back to water, to the liquid water. Okay, and these vapor molecules, once they are trapped, they exert more pressure than when it is open. And this also explains exactly what I said. When you have closed container and open container, the closed container will boil fast because the vapor is trapped, hence exerting more pressure. There are 3 videos here for demonstration, which is very important. Okay, so time will not permit me to play these videos, so ensure to watch these 3 videos. They are very, very important at demonstrating, the issue of the vapor pressure. Okay. I think the videos, one explain vapor pressure, there is also on cavitation. Okay, so please take your time to watch these 3 videos. Okay, they are very important. Okay, they will demonstrate the concept of vapor pressure, boiling, and okay. Engineering significance of vapor pressure in a closed hydraulic system, e.g., in pipelines or pumps. Water vaporizes in rapidly in regions where the pressure drops below the vapor pressure. Explained. When the pressure in the pipeline drops below the vapor pressure, water vaporizes. Okay, it vaporizes. There will be local boiling, and a cloud of vapor bubbles will form. And this phenomenon is called cavitation. And like I mentioned before, it can cause serious problems because the flow of fluid can sweep this cloud of bubbles into an area of higher pressure. And once it reaches of higher pressure, where bubbles will collapse suddenly, then there is huge amount of energy that is released. Okay, because if this occur in contact with a solid surface, various serious damage can result due to the large force with which the liquid hits the surface. The bubble, when it bursts, initially there is no bubble. Okay, when you have the pressure in the pipeline maintained above the vapor pressure, you have no problem. But it reaches a region where the pressure in the pipeline reduces below the vapor pressure of water, then bubbles will form. And this bubble, they will travel short distance and then encounter a region in which pressure is higher than the vapor pressure. So that will make the bubble to burst. And when this bubble bursts, they burst with a lot of force, large force, okay, that will hit the surface and will scour away or will eat away the surface. This occurs normally when you have, pumps and propellers, because of the fact that the pressure varies, at the upstream is usually lower than the downstream. So when it encounters lower pressure in the upstream, you have bubbles which burst at the other end. So you have pumps that need to be maintained because over time you realize they have been eaten out. I mean, they will be eaten because of cavitation. Yeah, and propellers. Okay, so cavitation can reduce the performance of machinery such as pumps, turbines, propellers, and the impact of collapsing bubbles can cause local erosion of metal surface. This is in this case in which you have like a ship propeller. Okay, you have like a ship um, propeller. Okay, in which you have an area in which there is like local erosion. The metal surface has eaten away because of cavitation. Okay, cavitations in a closed hydraulic system can be avoided by maintaining the pressure above vapor pressure everywhere in the system. Cavitation occurs when the pressure in the system falls below the pressure of water. That is, if the liquid is water. Okay, so once the pressure in the system, if you are considering, let's say, a closed hydraulic system in which the pressure can be, let's say, externally controlled, then the pressure should be maintained above the vapor pressure everywhere in the system to avoid cavitation. Okay, and there is video that can demonstrate this in this YouTube link. Okay, so open the video is very important. It demonstrates how cavitation occurs. Because of time, we may not be able to watch it. Okay, even if you just click,
Economics for our bachelor program in Renewable Energies and Environmental Technology. In this series, we are going over the phenomenon of cavitation water and its consequences. What is cavitation of water?
So this is the video.
Reach an environment.
Okay. So try to watch it, please.
Pascal, a certain mass of water where the bubble stops growing. If a brand new impeller to the left.
All right. So cavitation, from cavity, okay? It's called cavitation because they form cavities in the liquid. Cavities means holes, okay? Cavities mean holes, okay? Because they form cavities in the liquid in which they flow, where the pressure falls below the vapor pressure, okay? And it's an important consideration in the design of hydraulic turbines and pumps. Okay, very important in the design of hydraulic turbines, pumps. Let me see. Okay. So danger of cavitation in a propeller. This is just similar to what I explained before. The analysis of a propeller that operates in water at 20 degrees shows that the pressure at the tips of the propeller drops to 2 kilopascal at high speeds. Determine if there is a danger of cavitation for this propeller. Okay, so the minimum pressure in a propeller is given. Okay, and it is to be determined if there is danger. So the properties: the vapor pressure of water at 20 degrees is 2.32 kilopascal from the previous table. Now, this question we are told that the pressure at the propeller tips drops to 2 kilopascal. So that is below the vapor pressure of water, which implies there will be cavitation at that point, okay? But to avoid cavitation, pressure has to be maintained everywhere above 2.34, okay? At least the pressure everywhere should be minimum 2.34 and above. Once it falls below that, then there will be cavitation, okay? So pressure at the tip of the propeller is 2 kilopascal, which is the vapor pressure. Therefore, there is danger of cavitation for this propeller, okay? And we should know that vapor pressure increases with increasing temperature, and thus there is a greater danger of cavitation at higher fluid temperatures, okay? There is greater danger of cavitation at higher fluid temperatures, because once the temperature of the fluid is higher, then the vapor pressure is higher, and there is every tendency of fluctuation in pressure that the pressure within the liquid can go below the vapor pressure. And once that happens, you have cavitation taking place. Now, concept quiz: between pressure and temperature, which one of them is the most important factor for boiling to and why? Of course, we explained how the two play very big role. So here, sincerely speaking, I can say both are equally important. Okay, almost equally important, because whichever one you control will affect the boiling temperature. Okay, if you keep pressure constant and increase or decrease the temperature, that affects the boiling temperature, boiling point. Okay, or it affects boiling, as well as if you keep the temperature constant and vary the pressure, that will also affect boiling. Okay. The second question is, how can water boil at 25 degrees Celsius? The normal temperature, boiling temperature of water is 100 degrees Celsius at 1 atmosphere. So at 25, it means you have to reduce the atmospheric pressure to the vapor pressure of water at 25 degrees Celsius, which is what? The vapor pressure of water at 25 degrees Celsius is let's see. Okay, let me check from the other table. Okay, at 25, you have the vapor pressure to be 3.17 kilopascal. So at 100 degrees Celsius, you have the vapor pressure to be the atmospheric pressure, meaning if you want it to boil at 25, you need to reduce the atmospheric pressure from 101 to 3.17. So once, if you can do that, if you can reduce the atmospheric pressure to the saturation pressure of 3.17, then water will boil at 25 degrees Celsius. I hope it is clear. Now, water pressure and boiling. Okay. This is Mount Everest. Yeah, this is Jeddah. Like in Jeddah, it's atmospheric pressure, so water boils at 100 degrees Celsius. 1 bar is just approximately equal to 1 atmosphere. Yeah, 1 bar is approximately equal to 1 atmosphere. Okay, so this is the boiling temperature of water in degrees Celsius, and this is the pressure. At Mount Everest, the pressure is less. Mount Everest has about, it's almost 10 kilometers above sea level. 10, is it 10, 8,000 meters, that 8 kilometers above sea level. So the boiling point of water at Mount Everest, 72.3 degrees Celsius, because the pressure is less than atmospheric. Okay, the pressure has reduced from 101 kilopascal to 34. So once the pressure is reduced, the atmospheric pressure is reduced to 34, then water will boil at 72.3. Okay, and when you reduce the pressure further to 3.45, it will boil at 26.4. Okay. Now water phase diagram. So here we are discussing phase change, because once water reaches the boiling point, there is phase change. Phase, that is the state. Is it liquid, solid, or gas? Okay, so change in state. Okay, so vapor pressure is a pressure at which the liquid phase and vapor phase of material will be in thermal equilibrium. This I mentioned. Okay, and water exists in liquid or vapor depending on combination of pressure and temperature. Yeah, it's a combination. The pressure and temperature, all, I explained how they all affect the boiling point of water. Okay, and the boiling point here determines whether water is in liquid state or in gaseous state, that's in the vapor state. So the phase diagram, this is one of them. You can see this line. This is the boiling point of water, depending on vapor or below the boiling point, you have water in vapor phase. Above it, you have water in liquid phase. Okay, here you have pressure and temperature. So the combination, these two have to be combined appropriately before water changes phase. Okay, from one phase to another. For instance, if you're looking at pressure of, let's say, about 103, 101. Okay, this is the boil. Water will boil at 100 degrees Celsius. Okay, meaning when you maintain the pressure but reduce the temperature, water will be in liquid phase. When you maintain the pressure at 101 but then increase the temperature below 100, it will be in the vapor phase. Okay, that's why I said, when water cannot, once the boiling point has set, it cannot remain in liquid state, it will vaporize. Okay, so when you maintain the pressure and supply more heat, then it will all vaporize, it will be in the vapor state. Okay, while if you maintain temperature and reduce, if you maintain, let's say water at 80 degrees will boil at, when the pressure is about, okay, so when you maintain the temperature at 80 and increase the pressure, it means the vapor will be condensed back to liquid. Okay, so what will now be in the liquid phase. Is that clear? And at the same time, if it is at 50 kilopascal, when you maintain at 50 kilopascal, keep on supplying heat. Okay, then it means the temperature will increase and water will be in the vapor phase. Okay, this is important. You need to understand this figure very well and understand how to interpret whether whether water will be in liquid phase or vapor phase. Okay, this is all depending on the combination of pressure and temperature. Okay, and this is another one, a phase diagram for water. Okay, this is also for water. Okay, yeah, you have temperature, and then have the vapor vapor pressure here also in kilopascal. So above this line, you have water in liquid phase. Below it, you have water in vapor phase. What about along the line? Along the line, you have water in thermal equilibrium. That is, boiling is occurring along the line. Okay, so you have both liquid and vapor together because they are in thermal equilibrium. Okay, so liquid and vapor equilibrium along the line. So as shown, so this is just the explanation, as shown, water exists in the liquid phase for any combination of temperature, okay, that lies above the blue line. Similarly, water exists in the vapor phase for points below the blue line, okay. Along the blue line, liquid and vapor phases are in thermal equilibrium, okay. And when boiling occurs, the pressure and temperature of the water will be given by one of the points on the blue line. Yeah, this is very important. And this is another phase diagram for water. Okay, I told you the critical point, temperature and pressure. When you heat it, you can heat water up to 374. That is the critical point. Below that, we call it supercritical fluid. Okay, supercritical fluid. This is very important, most especially for mechanical and chemical engineers. Okay, and this is the triple point of water, in which in this case, at this pressure, and temperature exist in all states, in ice, liquid, so that is solid, liquid, and gas. Okay, because steam is just vapor. Okay, steam is just vapor. And at 1 atmosphere, you have water to be 100 degrees Celsius. That is the boiling point. Okay, and when you increase the temperature to 374, you have, this is the critical point of water. Oh, my time is up. No, I still have 9 more minutes. I still have 9 more minutes. It is 8 to 8:50. So you using the water phase diagram, explain what happens if the ambient, that is the surrounding pressure. Ambient is surrounding. Okay, if the ambient pressure changes at a constant temperature. So let's see what happens. Tell me. What happens if the ambient pressure changes at a constant temperature? Of course, I just finished explaining. Okay, when you have constant temperature, when the ambient pressure increases, let's say above 1 atmosphere, it will be in liquid phase. If the ambient pressure reduces below 1 atmosphere, it will be in the vapor phase. Okay, and if water temperature changes at a constant ambient pressure, if water temperature changes at constant ambient, so you are considering 1 atmosphere. Okay, at 100 degrees Celsius, it will boil. You will have both liquid and gaseous phase, but below 100 degrees Celsius in liquid phase, above 100 degrees Celsius at the same pressure, 1 atmosphere, above 100 degrees Celsius, it will be in the vapor phase. Okay. And how can water boil at 30 degrees? We just look at the vapor pressure of water at 30 degrees, which is 0.25 kilopascal. Okay, Newton per meter square is also Pascal. Okay, this is absolute. Yeah, absolute. So the temperature here is Newton per square meter. Okay, so the atmospheric pressure has to be reduced to this value. Okay, which is 4.2 kilopascal. Okay, the atmospheric pressure has to be reduced to 4.2 kilopascal. And once it is reduced to 2 kilopascal, it will boil at 30 degrees Celsius. This is the fluid summary of the fluid properties. Here you have density, specific, all that we considered: viscosity, surface tension, vapor pressure, bulk modulus of elasticity, their units, and how temperature affects each one of them, whether with the increase in temperature, the value decreases or increases. Study this table is like the summary of all that we discuss under this chapter. You see, in this chapter, we discuss a lot of the fluid properties, which are very important in subsequent chapter. The next chapter that we are starting now is fluid statics, in which will be applying the concept of pressure. Okay, we have introduced the concept of pressure here. Okay, but there we'll also look at the how fluid pressure varies. I mean, all that has to do with fluid pressure at rest, because it has to do with fluid statics. And then the next column, pressure effects, some common trends. Like when you increase or decrease the pressure, what happens to the fluid properties? Okay, and then how to get some of the fluid properties, the respective tables. So this is very important. Study this table is like a grand summary, all the properties and how they are affected by temperature and pressure. Okay, more often than not, like I mentioned before, for pressure affects usually gases. Um, uh, Pressure affects usually gases, but it affects liquids when you are talking about vapor pressure. But when you are talking about density, pressure just has little impact on the density of liquids, and that's why liquids are considered to be incompressible. Okay. Any question before we move to the next chapter? Okay, so let's move to the next chapter. Make sure to watch those video clips. They are very important. It's just because of the time factor, but I would have played them right here. Although I started playing one of them that describes the cavitation process. Take your time and watch they're very short. They are not long, but they're very important.
Assalamu alaikum, Doctor.
What was
Doctor, can you upload this chapter after class?
chapter 3?
Yes.
Yeah, I will upload it right after the class.
Okay, thank you.
Yeah, yeah.
Doctor, about the course tomorrow, 2.4 until 2.6.
What?
About the course tomorrow, 2.4 until 2.6.
Yeah, just I think.
How can I know? It is me, chapter 2
No,
that
from
you
the
upload.
textbook. From the textbook, open the textbook, section 2.6. That will cover, I think, surface tension, shear stress, and surface tension, probably.
Where
Okay.
can I find this test work, Doctor?
What?
Where can I find this test work?
Which work?
Test work, you said. Where can I find it?
Where can you find that?
Test work. You said test work from test work. So where can I find it?
The textbook is in the library, and you can even search it online. If you are lucky, you can get it online. Okay.
Okay, can you tell me what's the name of the book and which writer? Because I
The
am
name
not
of
a
the book.
حفاظ and I can find it in the library.
Okay. Check the syllabus. I uploaded the syllabus. Check the syllabus. The name of the book is there. Okay.
Oh, okay, thank you, Doctor.
And don't worry, I will even tell you the specific section. Okay, I'll mention it in the WhatsApp group now.
Okay, thank you, Doctor.
Yeah, you're welcome. And given that I have just 2 more minutes, okay. So here we have fluid statics. So here we will be dealing with a lot of statics. Okay, that's why even that is we are considering some of the properties of fluid at rest. Okay, so you need to probably review your start concept. You know, the free body diagram, the applications of equilibrium. These are the simple things that we are going to apply here. Okay, we'll describe pressure and pressure distribution, you know, and describe gauge, absolute and vacuum pressure, and list the steps used to derive the hydrostatic differential equation. And then we will apply the hydrostatic equation and the manometer equations to predict pressure, and apply the panel equations to predict forces and moments, and apply the buoyancy equation to predict forces. And then at the end, we will have some applications involving the atmosphere, the ocean manometers, and hydraulic machines, and how to find pressure values and distribution. Okay. I think I will stop here. But like I said, I will schedule another class to make up for the missed class last week. Okay. Last week, the first class we missed because there was issue with the connection here, and then the second class was missed because of National Day. Oh. Okay, and our major exam is coming up between week 6 and 7. We are still waiting to receive the confirmed schedule of the major exams. Once I receive it, I will post it on the group for you to know the exact date. Okay, thank you so much. And like I mentioned, for those that may be available, I will schedule the lecture. When I schedule it, you can see it, and then you can attend. But even if you don't attend, you find time to watch the video. You must find time to watch the video at your own convenient time. Okay? All right.